BBC Sounds. Music, radio, podcasts.
Hello.
Hello.
We used to be the centre of a conveniently small cosmos, with a sky made of crystal spheres and only the peculiar path of Mars to worry about. But as usual, science couldn't leave it alone, could it? No. So Galileo stuck his telescope in, spots some moons circling around Jupiter. Typically, the next thing you know, we're stuck in the backwater of a galaxy that's among 2 trillion other galaxies with billions of planets in each, and the universe is expanding at 70 kilometres per second per megaparsec. Did it sometimes make you hunger for a simpler time of inquisitions and where truth was found out through fear and torture?
So the moral of the story, as you see it, Robin, is that nature is unnecessarily complicated, and it would be better in any case if we knew less.
Yep, that's roughly what I'm saying. I want to go back to a time when you could settle neighbourly disputes by suggesting the lady next door was practising witchcraft. It was a simpler, more aggressively dogmatic time.
While Robin remembers his ducking stool with fondness, the rest of us will consider the magnitude and magnificence of the universe as revealed by science. What is the size of the universe and how long has it existed? What is the distance to the planets and the stars and galaxies, and what do we know about their histories? How do we measure the universe?
Joining us as we explore the universe, we have a distinguished panel of space explorers, and they are...
Hello, I'm Adam Masters. I'm a lecturer in planetary science at Imperial College London. And I think the most exciting discovery about the universe has been that there are oceans of liquid water underneath the icy surfaces of some of Jupiter's and Saturn's moons. And these are really good potential habitats for life.
Hi, my name's Jo Dunkley. I'm a professor of physics at Princeton University and author of a new book, Our Universe. And to me, the most remarkable discovery about our universe is simply how enormous it is. It's big.
Hello, my name's Jo Brandt, and I think the most remarkable thing about the universe is that there are oceans of liquid water under the surfaces of, was that Jupiter?
Yeah, that's right. Great answer.
And I didn't get to the end, but whatever you said, anyway.
And this is our panel. Jo, I suppose as the most regular guest on our show, you probably do have the greatest amount of kind of gravitas when it comes to understanding the universe. So I'll start with you, Jo Brand. How do you think we measure the universe?
Is it to do with expanding and contracting stars moving away from you or towards you? Thank you,
out.
Jo. Yes, apparently she's nodding. Adam's going, oh, not sure, because he doesn't know, because he's filling in from the show.
Jo.
Brian, am I right?
Let's find out.
That's pretty good, actually. Yeah, so it's actually kind of a challenge looking at and measuring the universe and seeing where everything is, because all we get to do is sit here on Earth and look. I mean, you can send some spacecraft out in the solar system, but we want to measure something much bigger. We'd like to figure out where everything is.
You've just dismissed Adam's entire career there, by the way.
Falling off the stage here.
Apart from this little thing that Adam does, we'll come to that.
We'll come to that, that's right. You know, all you can do as an astronomer or as a human is sit here on Earth and look out, and you see the stars above us. And they're kind of like just a two-dimensional surface around us. But what we want to do is figure out where everything is and how we fit into like a 3D picture of where everything fits in. And also, is it moving towards or away from us and where things are? And actually measuring the distances to things out in space is one of the hardest things that we have to do in astronomy.
Yeah, when did we first get any idea, actually, that the stars are very distant? Or even, actually, when were we able to measure the distance to the planets?
Well, so the distance of the planets, we've been able to see that the planets were moving in the sky. So we knew for like a long, long time that they were going around, that they were moving through the sky, and then we figured out they were going around the sun. But actually, it was only in the 1790s that people figured out how big the solar system is. And it was really cool, actually. It was through a transit of Venus measurement that this inspirational astronomer called Edmund Halley told future generations of astronomers that if they could only go and measure a transit of Venus when it's going in front of the sun, that they could actually figure out the scale of our whole solar system. And the way that works is that it uses this thing called parallax. So let's say you want to measure the length of your arm. Okay, so if you put your arm out in front of you with your finger stretched out, and maybe everyone can do this at home, it is now. Okay.
Unless you're listening to this whilst driving a car.
That's right.
Prince Philip.
want to measure the length of your arm, but you can't be bothered to go and measure it, you close one eye and see where your finger is against the thing behind it. And then close the other eye, if you can, and see if it moves, right? Do you see your finger move? Yeah. And if you then put it towards you and do the same thing.
I'd have measured it by this time, Joe. Because you can't be bothered to measure it.
You'll notice that it moves further if it's closer to your eye, right? So if your arm was shorter, it moves further. And all you need to know is the distance between your two eyes and the amount your finger moves. And you can figure out the length of your arm from that just using a triangle trigonometry that you might have learned at school.
And if any of our listeners, if you'd like to do that now and then send in your results, and we'll be able to work out who's closest. Because I'm sure there's someone at home who's going, my arm's 27 metres long. I've definitely done some measurement. I can't be Mr. Tickle.
That's right. So these astronomers, back hundreds of years ago, did the same thing using Venus as your finger and the backdrop, and they used Venus as it passed across the sun. And your two eyes were two different positions on Earth. So groups of astronomers would go to different parts of the world and look at Venus transiting the sun from two different places.
Halley proposed that, I think, in the 1670s, and it wasn't until 1761 that Venus crossed the face of the sun, which gives you a sense of the length of time, the importance of the measurement. There's almost a century, wasn't it? They had to wait.
But that
for
must
when
be
Halley
so
had realised
depressing for him. I know how we can work it out. When's the next one? I'll be dead. That kind of... the delayed gratification, of both theoretical physics and generally cosmology there's a certain almost sadness, but a beauty to it.
Well, I think it's amazing because we see it actually throughout the history of astronomy and cosmology that, he realised that it could be done, but that he wouldn't do it. And so he actually wrote this really inspirational paper that he wrote, exhorting younger people to go and make this measurement. And this is why.
So the transit of Venus means Venus going across the sun.
That's
does
right.
It?
Yeah,
as opposed to the transit of Norman, who's our builder, and he doesn't have any tools left in it overnight, just in case people were wondering.
So once that information has been gained, though, that's that done now. We don't have to keep waiting for the transit of Venus.
Right.
We've got the measuring tools. That's the starting point, isn't it, of then being able to get the rest of the view of distance of stars, etc. Is that fair?
That's right. So you step out. That's right. And so the next thing is, so once you know the size of the solar system, the next thing out is the stars. But it turns out you can measure the distance to stars also using parallax. But now, instead of two different positions on Earth being your two eyes, you look at a distant star that you want to measure the distance to, it's your finger again, and you look at the star against the backdrop of much more distant stars. And you close one eye by looking at the star from Earth at one time of the year. And 6 months later, when the Earth has gone around the sun halfway, then you look again at the star, basically closing your other eye, and you see how far on the backdrop it moves. So now you just have to see what angle the star moves against the backdrop of more distant stars, and you can actually find the distance to it. And you could never go there. So this is where you really can't go and measure your arm because you can't actually get to the stars to make that measurement.
It's a beautiful idea, isn't it? Because it's very, very simple, but it's basically the only way to do it. I was thinking, actually, we were talking about Venus, that in terms of measurement, we're talking about measuring the universe. Measuring or understanding the planets is also extremely recent. I mean, Venus, I remember Patrick Moore, reading that Patrick Moore, even in the 50s or so, and professional astronomers were imagining Venus might be a cloud-covered world and a tropical paradise. And it's not until we went there to make measurements that we found it was anything but.
That's true. I mean, picking up on this theme of having to wait a long time before the opportunity to make a measurement. Even within the solar system, if you think about the planets that are the furthest away, so Neptune's 30 times further away from the sun than we are. And we're about 150 million kilometers away from the sun, so it's a long way. So, at the moment, there's all of these plans to go to Neptune, and the earliest we could launch would be 2030, which in my field is pretty soon. And so you've then got 15 years, at best, if you want to orbit, to get to your target. So, I'll be retired. So even in planetary science, within the solar system, where things are closer than looking at stars and galaxies and things, we still have a long sort of time scale, and it's really the generation after me that's going to do all the science. So we get nothing for it.
Adam, you said you're working on designing those missions to Neptune. So what is that spacecraft? What would you like to know about the outer planets that we don't know now?
So, I mean, Neptune and Uranus as well, they're so far away. We've only ever had a snapshot with Voyager 2. So Voyager, as a mission, was 2 spacecraft, and they took advantage of very favourable celestial conditions, and they went to all the big planets. So everything we know about Uranus and Neptune is from one flyby.
Can I just ask, when something like that, when it's being planned, what are the kind of things that are being thought through in terms of going, this is the right time now to launch and send?
So if you want to get from A to B, where A is surface of the Earth at a launch site, out to, say, Neptune, then you care about things like, where's Jupiter? Because Jupiter's enormous, and a bit like if you've got billiard balls on a pool table and they collide and one of them comes off a bit faster, you can use that collision to gain speed. We call it a gravitational assist or gravitational kick. So one of the things you use to dictate your launch year is when's a good time to launch, swing around the sun a couple of times, use Venus in a similar way, for example, and then use Jupiter for a huge kick. That's the sort of thing that gets you going really fast. The problem is, the faster you're going, the more you've got to slow yourself down when you get there. And to do that, you need to fire the engines, and that's sort of one of the most risky and scary times after the launch is when you arrive, when you have to do that dangerous orbit insertion maneuver, which Cassini did in 2004.
Yes, we should say Cassini was the great mission to Saturn. How big a surprise was that when we got to Saturn and then with Voyager and other spacecraft at Jupiter, that we found that the moons themselves were interesting objects?
I think it was a huge surprise. So with these sort of missions, you plan things years in advance. So we know for a mission like the Jupiter Icy Moons Explorer that's being built right now, we know where it's going to be in 2031, to the nearest few kilometers. So you plan your mission based on what you expect to be interesting. And arguably maybe the biggest discovery in planetary science was the Enceladus discovery of liquid water. And Cassini was not planned around Enceladus at all. So that tells you how much of a surprise it was. They had to redesign the mission on the fly, orbit by orbit, using a bit of extra fuel to get closer. So, it was a big, big surprise. We didn't plan for it at all.
So, Joe, looking at the different kind of the distances we're talking about, are the clashes of ideology with, in your 2 areas that you're saying the magnitude of the universe itself, distances of galaxies, and then also, I suppose, in some ways, is it fair to say that there is, in one way, what we're really working at in that level of investigation that I'm talking about is kind of parochial. And do you get caught between those...
Classic Ince question.
I'm just wondering. Basically, I just wonder. Are things that are long, long way away better than things that are all close?
It's better.
No, no. I think you're trying to do different things. Goodness, you should of course go and look at the stuff you can get to. If I could get out and look at stuff that was further away, I would. But we just can't get to our nearest stars even. So we just have to look at them. And I'm interested in finding out what the big picture is, but the stuff we can go see, sure, we want to go see it. But I do think we're asking different questions about, if I'm looking out further, I'm trying to figure out the properties of the whole of the universe, then I have to not worry about the details so much.
So we've got out to the nearest stars. Parallax, this simple idea, with essentially blinking your eyes with a head, 180 million miles in diameter between the eyes. But how far can you get out using that technique, and then what do we do to get further out?
Yeah, so if you have a telescope just on Earth, then you can get a few hundred light years away from us. The nearest stars to us, star is 4 light years away from us. So you can get out beyond the nearest stars and into our Milky Way galaxy, which is the bigger thing we're part of. And actually, there's been beautiful measurements just this past year from the Gaia satellite, which can do the parallax measurement even better because it's out of Earth's atmosphere. So it can see thousands of light years, but you're still stuck in our galaxy. But
big enough for Robin?
Yes.
Is that big or little on your scale, Robin, the galaxy?
It's kind of middly.
So you can get out into our galaxy with parallax, but then you get stuck. And it's simply because the shift in position of the stars when the Earth goes around the sun is just too small to see. And so to get out further, you have to be able to do something else. And the something else, the next step, was figured out just over 100 years ago by this great astronomer called Henrietta Swan-Leavitt. She was actually part of this incredible group of women astronomers that are known as the Harvard Computers. They were employed by this astronomer called Edward Pickering, who realised that he could hire women at low cost to do great work. So that's what he did. He hired these women to study images of stars and to look for patterns in their behaviour. And she discovered this behaviour of this particular class of stars that let us see much further. And they're called Cepheid stars. And they're stars that change their brightness in time. They pulsate, they kind of shrink and grow in size. And she figured out there was this very specific pattern of these particular stars that the longer they took to vary in brightness, the brighter they were. And so the brightest ones might take weeks or months to pulsate in brightness, and the dim ones only days. What that says is that if you can just go and measure how quickly these stars are pulsating, you know how intrinsically bright they are. And then you look at how bright they appear to you from here on Earth, and that tells you how far away they are, because then if they're dimmer, they're further away. This was in 1908, and astronomers quickly picked up on this and used it to then figure out how big the whole Milky Way is, because they went and looked at these stars far out in our galaxy, and they figured it was like 100,000 light years across, pretty big. But then, even better, Edwin Hubble, an American astronomer in the 1920s, took this pattern, and he figured out that actually there were these like smudges of light in the sky that previously people had just thought were part of our Milky Way galaxy. And he found these particular pulsating Cepheid stars in these smudges of light and worked out that they were so dim that they had to be just way beyond our Milky Way. And he realized that they were actually galaxies beyond our own. They weren't in the Milky Way.
And do you actually still get, I know you're scientists and all proper and everything, but every now and again, when you think of the enormity of something which came from what we might say is almost nothing or nothing, do you still have those moments as you're collating those measurements of going, whoa, this is so big, and you have to kind of stop, and there's a little bit of kind of excited nausea?
Yes. You feel very small, but you just, as an astronomer, you try not to imagine all of it at once because it becomes overwhelming.
Do you find that, Adam, when you know that your spacecraft is out there and it's such a tiny thing, and if it's in orbit around Saturn or in the future in orbit around Neptune, those distance scales are so vast. I mean, do you feel that? I suppose you feel it in the amount of time you've got to design this spacecraft for. The engineering excellence of the thing, it's got to work for, you said, 15, 20 years or so.
Yeah, I mean, I would be lying if 150 million kilometres is something I can really picture. You can't. So you think about the system on a scale that makes more sense, as though you've made a little model in a box. But yeah, these sort of time scales, length scales, I've never really got my head around them, to be honest with you, and I think that a lot of other scientists would agree with me.
Joe, there's two Joes. We're going to have to work out a system. I've just realised this. Joe Brand, do you have those moments where the size of the universe becomes too daunting and you just have to stop for a second?
Not compared to me, no, not really. No, funnily enough, I don't actually have those moments, and I don't know why. I just feel a bit cross, actually, because what was that woman's name? Henrietta. You've heard of Hubble, you've heard of Halley. Who's heard of her? And it sounds to me like she didn't just look, and she actually thought and realised a pattern, you know. And I think it's kind of shocking when you go backwards to see how little. First of all, they were paid much less, presumably, and they were cheap to hire, as you said. But actually, a lot of them were obviously kind of very bright and really made a contribution. And I kind of find that upsetting, really.
It's interesting, yeah. Pickering did publish the paper with her name on it, which was not usual at the time, was it? So they did publish together. Pickering and Leavitt.
And I think it said that it was that he was writing on behalf of her, something which at the time was making
quite unusual. I would have thought.
Quite unusual, but at the time as well. But I totally agree, and the reason they were also looking at the images only is they weren't allowed to use the telescopes. Only the men could actually operate the telescopes because, of course, it's really hard.
Not some Freudian thing.
Well, they might have thought the women might get overheated by using a phallic symbol every day, as of course we would.
Well, I was talking, I think,
Bizarre.
but Brenna Hassett, who runs a thing called Trailblazers, which is kind of celebrating a lot of the, for a long time, forgotten women of things like paleontology and archaeology, says quite often you find these old papers from the 19th century which say, and thank you very much to my wife for typing this out, which actually means, and thank you very much for my wife for writing half of this, but I'm not going to say that. No way. It makes my moustache droop.
I think there's also some efforts to try and... So in astronomy recently, the pattern that she figured out, now it's being increasingly referred to as Leavitt's law. And as in the astronomy community, we are trying to acknowledge that more. But it's still true that the history of astronomy... And at that time, she was part of this group of women, the Harvard computers, but a bunch of the other women in that group also made great discoveries, and we haven't really heard of them either. They classified the stars, like all the way in which we understand how all the stars in the sky are different. They were classified by these women as well.
And can I just ask you one more thing? I mean, as a woman working in that field today, do you feel there are sort of any differences still between men and women working in your science?
Well, I don't think there's a difference in how clever we are, but...
I didn't mean that.
Yeah.
I didn't mean, are you a bit thick and all the men are very intelligent? No, I meant in terms of, women do kind of get patronised in male, is it still male-dominated? It is?
Yeah.
And I think women do have a tendency to be patronised in those areas, don't they? That's what I meant. I can tell you're brighter than all of them. But, do you find it difficult in any spheres of work?
Yeah, I do. So there aren't enough of us. There's there's maybe 20% or fewer women, and actually as you get more senior, there are even fewer of us. But it's increasing. It's increasing. So I feel
going in the right direction.
It's moving in the right direction. So I feel optimism, but I still, work to be done.
So we've got the stars that we can see, that we know the intrinsic brightness of them, so we can measure the distance. But that doesn't go in any sense all the way out to the edge of the universe. So what do we do for the final step? Because we want to get to the size of the universe.
That's right. So these Cepheid stars take us out beyond the nearby galaxies around us, and it takes us even out to further galaxies. But it doesn't take us out to the furthest reaches of the universe. And for that, to get even further, we use supernovae. So these are now not pulsing stars, these are exploding stars. And it's what happens when quite a unique star called a white dwarf star gets a bit too heavy and then explodes. And our sun will turn into one in about billions of years from now. And they're so bright, the explosions, that they briefly outshine an entire galaxy of billions of stars. So they're so bright that we can then see incredibly far away out to the more distant galaxies. And that takes us out billions of years back in time.
So we need, before we move back probably locally to the solar system again, we need the final answer. So we're talking about measuring the universe. So how big is the universe, the piece of the universe we can see? How big is it?
So the observable universe is just the part that we are able to see. And so it's by definition centered on us, because we are just able to look out and we can just see a finite amount. And so why can we only see a finite amount? It's because we actually now think that the universe has a finite age. It's only been around for a certain amount of time, 14 billion years, roughly, more or less. And so we can actually only see out as far as light has had time to reach us in that 14 billion years. So you might then naively think that the distance to the edge of the universe is 14 billion light years. It's actually bigger than that because the universe has been growing that whole time. So it's more like between 40 and 50 billion light years out to the edge of the observable universe.
Has the universe actually got an edge?
No.
But so you're saying the edge in terms of what we can see?
That's right, yeah.
So what's over the other side? Just more of the same?
Probably.
There's not like a service station or a...
It's one of the big questions, isn't it? Whether it is infinite or not. Would it bother you, actually? Because it's one of those things that when people seem to get upset. Sometimes when I talk to them, they say, I can't comprehend an infinite universe. I'm happy with the finite one that's way bigger than, 50 billion light years in every direction.
I think an infinite one is quite upsetting.
There's something, isn't there, about infinity that's unsettling in a sense.
There is. And there's also something about the limits of our brains, mine more than yours, I'd imagine, but trying to visualise something that goes on forever is really hard to do in your head?
I certainly don't feel particularly comfortable with an infinite universe. The nice thing is that there is a possibility of it being finite, but still without any edges, because it's possible it's all wrapped up on itself. So in the same way that...
I've never seen Jo Brand look as comforted as she does now.
I wish I'd brought some benzodiazepines with me. It's all right, no one knows what they are.
Well, that would be like the surface of the Earth, wouldn't
That's
it?
right. So the idea, the surface of the Earth is finite, right? So there are no edges to the surface of the Earth, but the surface of the Earth is only two-dimensional. So we think it's possible that the whole of space is finite in the same way, but now you've got to imagine having the edges wrapped up but in 3 dimensions. And our brains can't do that because you see the surface of the Earth in 3 dimensions. And so if you want to visualize 3 dimensions, you need a 4-dimensional brain, which I don't have. But it's quite possible that if you...
I have. Imagine if I did. That'd be so brilliant.
If that was true, then you could go out any direction in space, so out that way, or out that way, or out that way, and you'd end up coming back around where you started.
Listeners at home, you may now take your red pill.
Adam, is that why you stick to close by, sort of rather reassuring planets? I would do as well,
Absolutely, yeah, as a career choice.
So Adam, we talked about the measurements that essentially all we have is light there. So we've talked about the vast amount that we can do by looking at the light from distant stars and galaxies. But what sort of measurements beyond the cameras? And the cameras are things I think everyone thinks about on space probes. But beyond that, what are the sort of instruments we're putting on space probes, like Cassini at Saturn, Voyager perhaps, and the new probes to Neptune?
I mean, we have a whole range of different types of instruments that we have flown and plan to fly and are currently flying on different missions. First thing to say is actually a lot of really high-profile, very, very exciting and successful missions like the Hubble Space Telescope. That's a mission that bridges the gap between Jo's field, which is much, much bigger, and also solar system science, where Hubble's allowed us to do some really great things, looking at Jupiter's aurora, for example. And on a spacecraft, you have your cameras. They're always on there, especially if it's the first time you go into a system or one of the first few times. You have instruments that measure particles, so you have electrons and ions whizzing around in space around a planet. That's something you want to measure. It can also tell you something about the surfaces of the moons. Sometimes you get particles that come from moons or planet's atmosphere. You don't just care about the visible wavelength, so you have images in other wavelengths, which is something that astronomers really started, looking in lots of different wavelengths, but we also do it in the solar system. Magnetic fields, I mean, you can get a sense that this is the list that's going to go on and on and on. Dust, radio waves, everything.
I think the magnetic fields are interesting, aren't they? Because a question you mentioned at the start that the greatest discovery, you think, or one of the greatest discoveries is the discovery of oceans of liquid water below the surface of moons.
Oh yeah, I said that as well.
Yeah, you said it. As Jo also concurred with that analysis. But we didn't land on those moons. Mm-hmm. So how did we know?
So the short answer is there was a magnetic field that was measured that was unexpected. So when you fly with a spacecraft that's got a magnetometer, is a bit like a compass in space, and it tells you which way locally the magnetic field points, so just a three-dimensional compass. So you have an idea of what you expect to measure. You're going to a big planet like Saturn, let's say, which Cassini did, and Saturn, like the Earth, has a big magnetic field. Really, like lots of energy in the core, dynamo action, producing a huge magnetic field. So you expect to measure that. So then if you measure something else as well, so if your measurement is different from your prediction, then you've got to explain what causes that difference. And that's where the Enceladus discovery came in. So the magnetometer team, led by Michelle Doherty, who's also based at Imperial, same as me, they identified a magnetic field signature near Enceladus that just shouldn't have been there. And that's the beginning of then showing that magnetic signature is because the magnetic field is having to bend around this plume of water that gets ionized in space and presents an obstacle to the field. So it's a really powerful, effectively remote sensing tool, because the magnetic field's a three-dimensional field. It's invisible, but it responds to things.
Is that
like
the only thing it could possibly be then, water? Could it not be something else?
Well, since then they've gone and measured that it is actually water. So it began with looking at the signature. But actually, it's a good question, because at Jupiter...
Thank you, Adam.
Because at Jupiter, where we don't necessarily have plumes of water erupting out that Cassini was able to fly directly through, at Jupiter, another spacecraft, Galileo, saw a magnetic field that was changing with time that shouldn't have been there. And that's a magnetic field arising in a water ocean underneath the surface that we've never got anywhere near. But we know it's there because it's the only explanation for why that magnetic field's arising. So we think that similar to when you're at the airport and you go through a metal detector, you've got a system there where electric current flows and it generates what we call induction in anything metallic. Anything conducting in your body is then going to have a magnetic field. It generates itself. So that's effectively what's happening at these Jovian moons. You've got a big background field that's changing. Electromagnetic induction happens in a water ocean that's a little bit conducting, just enough, and it gives you this field you didn't expect.
And that's Europa, the moon Europa.
Europa, but also Ganymede. Ganymede's another really interesting one. Those two, and possibly also Callisto. So these are 3 of the 4 so-called Galilean moons, the really big ones. I mean, Ganymede's about the same size as Mercury, so these are enormous moons.
Planetary-sized moon.
Can I just ask one thing as well? Are there times when, like you said, it couldn't be anything else? But are there times in science where people have thought it couldn't be anything else, and it was something else they didn't know about, and there's some kind of flaw in the deductions, and they're not right because there's something that you don't know yet, for example?
Absolutely. I mean, sticking with Cassini as a sort of case study, we mentioned that Saturn's got a big magnetic field like the Earth, but the properties of that magnetic field, and we characterized its sort of orientation and how it changes with time, is a violation, apparently, of our basic understanding of how planets generate magnetic fields. So we had a hypothesis, a prediction, and then when you go there, you measure a field which doesn't conform to that. And we're still trying to understand exactly why that is. So there's plenty of occasions, and that's actually what you want. When you launch a mission, you plan to answer a load of different questions, but the biggest discoveries are quite often the unexpected ones.
Can I ask you that, because I think a little more than a week before we recorded this, the Saturn news was about the rings of Saturn and finding out about their age compared to Saturn itself. So how has that been discovered?
So the only way they were able to make that big discovery about the age of the rings, which is based on the total mass of the rings, which is based on gravity measurements, you needed to get very, very close to see the difference in the spacecraft velocity compared to what you'd expect. That's how you determine the total mass of the rings. They only were able to do it right at the end of the mission. We had this fantastic grand finale, as they call it, where we had 20-something dives between the rings and the planet, and at the end of it, we burnt up. And so we're still doing science with that data now. I mean, big science, big discoveries, and that's going to continue for many years.
And we found out the rings are possibly only a few, even tens of millions or hundreds of millions of years old.
That's right. So the total mass of the rings is a big factor here, because the more massive they are, the older we'd think they'd be. So the mass tells you they're younger, but also the brightness of the rings is another clue. That came a bit earlier.
Yeah, so the dinosaurs, were they in possession of a telescope, would not maybe have seen Saturn's rings because they might not have been there, which is a remarkable thought, isn't it, about
amazing.
Saturn? What?
No, I just like that image. You put a lovely image in people's heads.
Dinosaurs.
Of a Tyrannosaurus Rex going, I've made the telescope, but I can't get it to me eye. It's a beautiful kind of... I haven't thought this through at all.
I kind of like that idea that it made it, and when I was told Saturn was a very beautiful planet and there are no rings there at all. Which is a temporal problem as well with that, isn't it? Yes.
Can I ask you one really, really quick thing? You know when people name their relatives after a star, do they really do that? Or so, can you look through a telescope? Because I name one after my mum and go, oh, look, Joyce Brand's looking particularly bright tonight. Does that actually happen, or you can't? No, I knew it didn't.
Yeah. There are some rules. Some people name things after themselves, relatives, but there are some naming conventions.
Yes. So that's all a big con, isn't it, then? That star, whatever it's called. Has anyone here done it? Let's all gang together and get our money back, then.
That's what I like, the speed in which you can turn this show into That's Life.
I just wanted to ask you, just on that last question, Adam, just one final thing. How do we name those? So there's the thing that New Horizons spacecraft went to after Pluto. Pluto itself's a good example. So these are objects that are discovered in modern times that are part of the solar system. What's the naming process?
Well, Greek mythology is always our go-to, but we're running out of deities. So now you've got a lot of very unimaginative names. I mean, even missions. So a lot of missions like Galileo was the Jupiter mission, which makes sense. But now we're getting to much more boring names. I mean, the next big Jupiter mission at the moment is Jupiter Icy Moons Explorer. You know,
I'm just checking
much
if there's
less
any
grand,
mistake.
much less grand, but at least it says what it's going to do.
Can't we name it after anything that's been in a Ray Harryhausen movie? Because they're great, like, you know, Jason the Argonaut stuff. Let's broaden out in terms of the myths that can be used.
Well, I have to say that there's lots of different mission proposals out there. They get proposed all the time, and some of them are pretty crazy. But what's quite interesting is the discussion about naming the mission is sometimes longer than the discussion about how to get from A to B. And it's always, you know, Delphin was the leader of the dolphins in Greek mythology or something like that, and then there's a big discussion about it.
Can you name a mission after my mum, seeing as she'd be really disappointed after she's heard this show?
Right, anyway, so we asked the audience, if you could live anywhere else in the universe, where would it be and why? And they answered, I would live on the moon, so I could eat my body weight in cheese every day and remain weightless.
A galaxy far, far away, cos Princess Leia.
Brian Blessed's lungs. Lovely and spacious, although it's a bit of a dive!
Mars. Why? No humans. And, most importantly, no flat earthers. Also, I've seen Matt Damon in The Martian several times. I'll be fine.
Wouldn't it be terrible if Thomas, who wrote that, actually got to Mars and looked back and went, oh, bloody hell, it is flat. Anyway, so Brian Cox's Barbers, where magic really lives.
How about this one? The other side of the moon to surprise the Chinese. That's good, isn't it? That's from Jem. Well done, Jem.
So, anyway, thank you very much to our panel, Adam Masters, Joe Dunkley and Joe Brand. And this is the last episode of Series 19, which will be the last prime-numbered series of The Infinite Monkey Cage until 2021.
The prime factors of which are 43 and 47. At which rate, 2 series a year, that means that it will be broadcast when?
Send your answer by postcard only to The Infinite Monkey Cage, beneath the crystal spheres, just above the elephant, but not too close to the turtles, Earth.
You've not been paying attention, have you?
Not really. No one has. They just hear your lyrical voice and they go, ooh, it's a lovely sound. I don't know what it means. Goodbye.
In the infinite monkey cage. Now nice again.
OK. If science podcasts are your thing, but you've run out of monkey cage supplies, or you've just had enough of Brian Cox, how about something a little bit different? The possibilities are infinite, of course, but you could try my Life Scientific podcast. I've spent 7 years interviewing some of the finest scientists alive. I've talked to people who've climbed into volcanoes, analysed the teenage brain, and invented the batteries for your mobile phone. Black holes and bacteria, robotics, genetics, fossils and Formula One. It's all there. The Life Scientific podcast is a collection of in-depth interviews with brilliant men and women whose work is changing our world. That's The Life Scientific, hosted by me, Jim Al-Khalili. You can download it from BBC Sounds.